And welcome everybody to the first of 10 webinars in the GPM 10 in 10 webinar series. Tonight we have myself. I'm kind of serving as the MC for this. My name is Dorian Janney, and I am the GPM outreach coordinator. And I also have pulled together a lot of resources that I will be putting in the chat window from time to time. So you have access to a lot of extra resources that will help you better understand and share what you're learning with others. We have behind the scenes, my left hand, and I'm left-handed, and that is Andrea Portier. She is the GPM applications coordinator, and tonight she's serving as the technology guru behind the scenes. Thank you so much, Andrea. And she'll be monitoring the chat box. I'll be looking at that as well. We will try to make some time for questions, but we want to stick to our time. We're giving each of our guest speakers 15 minutes. So if we don't have time for questions when the speaker is finished, the speakers will remain looking at chat and answering your questions so that we'll make sure that we don't neglect you. Our first speaker is going to be Dr. George Huffman, and he is my boss, and he is the supervisory research physical scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland, where he is the project scientist for the Global Precipitation Measurement Mission and the lead for the GPM multi-satellite algorithm team and the chief of the Mesoscale Atmospheric Processes Lab. And if that's not a mouthful, I can't tell you what is. After George, we're going to have Candice Carlise. She is the GeoXO Program Flight Project Manager. In this role, she manages the spacecraft and instruments through formulation, development, launch, and on-orbit checkout. Candice was, excuse me, the Global Precipitation Measurement Deputy Project Manager, beginning in the formulation phase and continuing through successful handover to mission operations in May of 2014. Dr. Scott Brown is our final speaker, and he is a research meteorologist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. And he specializes in hurricanes, convective storms, and winter storms. Scott is the project manager for the Earth System Observatory Atmosphere Observing System, which you'll be telling us about, and he was the project scientist for the Tropical Rainfall Measurement Mission. And so with that, I will now stop and I will bring to the stage Dr. George Huffman.
Thank you. And now we'll see how the technology goes.
There we go.
Share the screen. Find my cursor.
And I will remain unmuted, George, until your slides are up, and I will let you know that they're going just fine. So
okay,
you don't have an empty void.
And so you can hear me okay?
You're just fine. Yep. Okay.
Well, I'm pleased to be here. Thanks to Dorian for the introduction. This is NASA. You can't have NASA without a bunch of jargon. So you've heard some of the jargon already related to me. The project scientist means that I am in charge of the science team and sort of the overall, results of the mission. Somebody else at NASA headquarters is in charge of money and stuff like that. Even ultimately, there's my email address if you're interested in corresponding with me later.
George, we're not seeing your slides yet.
Oh, yay. Because I didn't do this. Let's try this.
Always something.
Is that good?
No, I don't see them yet, but I'm hanging in. I'll let you know when I see them. Something's happening, George. I'm seeing your slides. It's all good.
Okay.
As you were.
Technology. Can't live with it. Can't live without it. The background on these slides, which is reproduced in living color to the upper left, is the logo for the mission. The logo was very carefully chosen to be the shape of an actual raindrop when it's big. they get hamburger bun shaped like that. And the Goddard Earth Sciences is the group of the next administrative unit under which I work. So let's get started. Let's get started. There we go. Okay, so I just want to give a graphical biographical sketch. This is the representation of the climatology of precipitation over the US. But I use this as a platform to show where I've been. Weather is cool and relevant and funded. That last one is really important if you want to make a career out of it. I was hooked in like 4th grade, and I found along the way that it requires lots of math and science. It takes a lot of computer skills, and it takes English. I'm talking to students, I always say, don't go into meteorology or any other science if you want to avoid English. I use it all the time. So I started out in a little consolidated school district called Mapleton in Ashland County, Ohio. It's possible some of my classmates actually got on tonight, I'm not sure. After I graduated from high school, I went to Ohio State. It was sort of a contrast. I went from a class of 96 graduates to one of the largest full-time campuses in the country at the time. While I was there, whoops, there you go. I had a chance to go to the National Center for Atmospheric Research, which is a nationally funded atmospheric, meteorology program in Boulder, Colorado. I learned to do meteorology in shorts and hiking boots, and it was a really great experience. After that, after Ohio State, I went to MIT, got a PhD in meteorology, lived through the blizzard of '78 up there in Boston. I went to University of Maryland College Park, where I was on the faculty of the meteorology department for 6.5 years. And then I went to Goddard and started doing global precipitation after I did a few other things. 24 years of contracting and university affiliation, and then I joined civil service in 2012. Okay, so here's the driving down the road in the snowstorm logo. This is a joint US-Japan project. JAXA, the Japan Aerospace Exploration Agency, is our partner. They provided the radar, and GPM, the NASA side, provided the launch or the spacecraft and the radiometer. So here's a picture of the core observatory, a depiction on orbit. This is sort of the only satellite we control, and talk more about that in a minute. It was built at Goddard in a giant clean room we have. If you know about the James Webb Space Telescope, that was built in the clean room recently. So this is some dozen years ago. It was launched in 2014 from Japan on a Japanese H2 rocket. It's in a 65-degree inclined orbit, so it doesn't go from pole to pole. It goes around the Earth at a slant 65 degrees. Every 83 days, it goes through, it changes the time of day that it does observations. So every 83 days, it goes through a complete cycle of that, which means we see every part of the daily cycle. So the two sensors I mentioned, the microwave imager, it has a 2D depiction of the data, and it has a wide swath. It was built in the US, Ball Aerospace. And then the dual frequency precipitation radar, which is a 3-dimensional, radar image, and it gives you a narrow swath, and that was built in Japan. Oh, and there's where they live. So the microwave imager is this sort of barrel-shaped thing, which is, let's see, I can do better than this, right? Yeah, laser pointed, there we go. It's this barrel-shaped thing. This reflector spins on a vertical axis and then gives a view of the Earth at a slant that goes down into the sensor. The other thing is the dual frequency precipitation radar. There's this huge box here. It's big. It's like 2 by 2 meters by 1/2 meter. And then there's a smaller box up front, which is almost invisible under the front of the satellite, which is a higher frequency radar. And if you stay tuned for Candace, which I spelled wrong, sorry, Candace, she had a really cute visualization of what it took to go from pieces of metal and foil to this satellite. Okay, the second part of GPM is the constellation. The idea of GPM is that we want to improve knowledge of the water cycle variability, and we want improved prediction of floods and landslides and freshwater resources. To do that, we need more satellite observations than the core observatory. As you'll see in a second, you just don't get much data from a single satellite. And so we work with a bunch of other agencies in the US and abroad to get more precipitation relevant so-called satellites of opportunity, which is to say, they're running the satellites for their own purposes. They send us the data. Currently, we have 11 of these others. And so the GPM core observatory is up here, and then we sort of list the others. Notice the flags. We got Japan, France, India, and the European Union. This is GPM by itself, core observatory. Pretty lonely. Here it comes again. So we invited all the other guys to send their data. And this is what it looks like when you add a whole bunch more satellites to get data. If you speed it up a little bit, just to give you a sense of what's going on. Sure enough, you get coverage, but it's still sort of jerky. And so I lead the so-called iMerge algorithm that does the final time interpolation that fills the gaps and give you this kind of smooth activity. Besides passive microwave, we also use geosynchronous infrared data, what you see on TV every night as clouds. We can also get some very approximate precipitation estimates from that. So here's an example of a flash flood event that happened in the Washington, D.C. area. This is back in 2019. Nice little visualization. So the broad scale picture that you see here is iMerge. And we're going to pause it when we get to an overpass that happened to occur from the core observatory. And so the three-dimensional that you see is coming from the radar. And what you see is, notice all that blue stuff at the top, just like the visualization that Dorian was showing at the beginning, before things started, that's snow. So even in a summertime heavy rain situation, when you go up high enough, about 5 kilometers or so, it's snow. And what you see is that, it's the really heavy rain is toward the bottom of the column. The light and dark purples get stronger as you go down. It's really sort of typical of these heavy flood events. So once in a while, we get lucky and we actually get an overpass of an event like this, and it's really pretty cool. Another way we can use the data is to track tropical cyclones, hurricanes, typhoons, and tropical cyclones, as they're called in the Indian Ocean. This is an example of tropical cyclone Freddie. It was February of last year. It's in the southern hemisphere, so they get the tropical storms in their summer. That's our winter. And so this is an example. It started between Indonesia and Australia. The white-gray shading is that IR cloudiness I talked about. iMerge looks through the clouds and shows precipitation. And we're showing it 2 different ways. The greens and purples are accumulation. In this case, the blues and yellows are instantaneous rain rate. And so it goes crunching along across the Indian Ocean, not bothering anyone, then slams into Madagascar, death and destruction and ensue. Then it goes across and hits Mozambique. What made Freddie special is it sort of wandered around. There wasn't much to it, but it kept it, started together. Here it comes back offshore from Mozambique, almost back to Madagascar, and restrung things and became a tropical cyclone, a really bona fide tropical cyclone again. And so the forecasters know to look for this kind of stuff. They kept tracking that remnant. And so it became a tropical cyclone and slammed into a different part of Mozambique. So one country got slammed twice. And we could depict this not only over land, which after all, there's at least a few rain gauges around pretty much every place. We can also show it every place over the ocean. So one of the really strong points about satellite data is you can see what's happening before it gets to land. You already know not just the fact that there is a tropical cyclone, but sort of what the rainfall characteristics are before it ever hits. It takes a lot of people to make this stuff go, and this is a broad scientific activity. And so we're really trying to, not only do the science, but also do applications. So this is the science team from last fall's meeting. Just real quickly, we send out a lot of data. For those of you that know data, know why things like, computer storage kind of stuff, on the right-hand side, we send out somewhere over 200 terabytes of data a month to users, both scientific and applications. In terms of number of users, we're over 1,000, well over 1,000. Applications, what's that mean? Well, it's a lot of different things. So landslides, hydrology, you can sort of see what the division is. And there are specific areas that we concentrate on. So for example, health, you might not think of that, but if you have a really heavy rain event over a long period of time, suddenly you start having mosquito-borne diseases. Okay, so I've pretty much shot my time. So I'm gonna wrap up and get off here. My closing remarks, so this is the visualization you saw before. I don't even have to describe this very much because Dorian did such a great job before we got started. The core observatory, the main, the only satellite that GPM controls, is functioning well. And the JAXA-NASA partnership has really been very effective at, bouncing back and forth between, they tend to emphasize the radar data, we tend to emphasize the microwave data, but we all use it all for various things, depending on what the research project is or the application. GPM is contributing significantly, and at this point, the forecast is that we're going to go into the 2030s, maybe 2031, 2032, before we run out of fuel, which is used to keep the satellite at a certain altitude, and then it will have to eventually re-enter the atmosphere. So I look forward to seeing how the legacy of TRIM, which you'll hear about from Scott, and GPM continues into the AOS area, which you also hear about from Scott. Once again, there's my email address. There's the website for GPM. That's everything GPM documentation and examples and stuff. And then finally, at the bottom of the visualization is the URL for this particular visualization. It's updated every hour around the clock, 24/7. And with that, I thank you for your attention, and I'm going to turn it back to Dorian.
Wow, George, that was absolutely incredibly impressive to be able to fit so much about the Global Precipitation Measurement Mission into a very condensed and beautifully presented 15 minutes. So I am in awe. And I noticed that in the chats that really it was there weren't questions per se. It was more just people saying thank you and thank you for such a great presentation. And also somebody mentioning that warming waters increases the severity of these storms. And indeed, that is true. And do join us a little later when we're having one of our webinars that focuses on weather, and then also looking at the difference between weather and climate. Yes, we will put that link up there for you. And also, yeah, excellent. We will make sure that we do that. So let's go ahead then and hear from Candace Carlisle and learn about the engineering behind this amazing satellite mission. Thank you, Candace. And I'll stay on and at least with my sound and let you know once I see your slides and that you're good to go.
Alrighty, give me 1 second here.
Of course.
All right, whoops, we're on the wrong page. So I got to get back to the right page.
Just keep us honest. Perfect. You're good.
Okay, got it?
Yep, we're good to go.
All right, good. So since George did a bio, I'll do a mini bio. I majored in physics and computer science at William and Mary, and I've been at Goddard just over 40 years, believe it or not. I worked on GPM from 2006 until 2014. And I had a lot of fun walking down memory lane to put together this webinar. So here's a little background on GPM. You can see in the upper left some of the major portions of the core observatory. George already pointed out to you the two instruments. We, of course, have the solar rays that provide the power for the spacecraft. It has a propulsion system and reaction wheels, which are what keep it on track of where it needs to be. That high gain antenna you see, the white thing, is what it uses to communicate all of the data. It was the largest spacecraft built at Goddard. And I have some size comparisons there. Tip to tip, that wingspan is about the same as a corporate jet, about 43 feet. And then the front to back is a similar length to a Ford Explorer. It is about 21 feet tall, that's 6.5 meters for metric fans. And it's about 3,850 kilograms or 8,500 pounds. We built it at Goddard with components that were purchased from contractors around the world. And we also had a Japanese contribution of the precipitation radar. Japan also contributed the launch vehicle. We'll hear more about that. And the US instrument was that microwave imager that you can see here. This is GPM in a minute. And it begins with building up the spacecraft itself. And those large boxes are the precipitation radars, those large white boxes. That there's your high gain antenna. You can sometimes see the GMI instrument spinning. That was a quick little solar array deployment there. There was the GMI instrument spinning and the high gain antenna moving around. Flying to Japan. This is at Japan, getting checked out. And launch. So maybe that was a little bit fast. So I'll slow things down a little. Here are some photos of the GPM being assembled. On the lower right is the configuration that it would fit inside the launch vehicle. So you know launch vehicles are kind of tall and skinny. So you keep everything all smushed together and then you deploy it later on orbit. The other photos I put in so that you can see kind of the size of people next to some pieces of the observatory. We do a lot of testing at Goddard and we have a lot of test facilities. And the reason for that is to make sure that the spacecraft is completely ready for everything that it needs to do in space. That facility you see there on the upper right does electromagnetic compatibility and interference testing. And what that does is make sure that nothing on the spacecraft interferes with anything else on the spacecraft, kind of like when you try to run your toaster and your microwave at the same time, say, or your radio and your microwave sometimes, or that it won't get interfered with by anything that it can see in its environment. We do vibration and acoustic testing to make sure that it'll survive that ride in the rocket, which is very loud and shaky. We do deployments like you see in the lower left to make sure that everything will go from that stowed configuration to the extended configuration. It'll need to be on orbit. And then we do thermal vacuum testing, which is in vacuum and takes it to the extremes. So in the upper right, you see that thermal vacuum chamber, and there's actually a little GPM on the top of it. So that shows you how big that chamber really is. And we tested that in the chamber with a lot of functional testing over the period of 36 days. And it went from minus 10 C to about 40 C, which is about 14 degrees to about 104 degrees Fahrenheit. Then the observatory was flown to Japan in a C-5 military cargo plane. I went to the Tanegashima Space Center, where we checked it out and then integrated it with rocket and enclosed it in that rocket fairing. And that is what you see on the lower left there, that the fairing is being lowered over the GPM spacecraft. So that it was launched February 27th in US time. And at launch, there was half of the team was in Japan taking care of the spacecraft. And then the other half of the team was in the US. So I was on the half of the team that was in the US. And so the top two photos there are of the launch day. And we were in what's called the launch control room, talking to the spacecraft. And they tell a story about how, you know, other people in Tanegashima, they all start clapping when the rocket takes off. And everybody in the launch support room was quiet. And somebody asked, you know, why are they so quiet? And the reason is they're waiting for the spacecraft to talk to them, which is true. We were all sitting there waiting with bated breath for the spacecraft to talk to us, which it did. And so we were all very happy that it was working. And the picture on the right of all the people with their thumbs up, that was a few days later when we tested the GMI instrument successfully. And we all worked 12-hour shifts for a little while after launch, making sure everything's checked out. And so in early March of that year, there was a snowstorm. And I actually took these snowstorm pictures. You know, you see the professional pictures at the top, but I took the snowstorm pictures of everybody coming in, ready to work their shift, very dedicated, and just prepared for whatever might happen there. So one of the most interesting aspects of this mission was the cooperation with Japan. So the upper right photo is of the NASA people on the left, Japanese people on the right after a successful design review. The picture on the upper right is a successful safety review that was held for one of the secondary payloads. Now, in addition to GPM, that rocket had 5 smaller payloads on it, and they were mostly from universities. So this is actually one of the university teams that had a very small payload on that rocket. On the lower left, you see one of the Japanese team members built a 3D hurricane model with Legos. And actually, I was at a conference recently, and I saw somebody had built a 3D hurricane model with Legos, and I knew where they'd gotten that idea. The center is actually the town of Minamatani in Tanegashima, Japan. And those were the yellow banners that were welcoming us into town when we showed up with GPM. And the bottom right is a Japanese custom that's coloring the second eye of a Durumidal. You see, with a Durumidal, it has 2 empty eyes. And when you set a goal, you color in the first eye. And then when you achieve the goal, you color in the second eye. So that is coloring in the second eye of that Durumidal to show that GPM goal was successful. In addition to working with the Japanese and going to Japan, we also got a chance to explore the Japanese culture, and that was very, very rewarding. The upper left photo is a group of us in Tanegashima of the combined Japanese and US team members that went to a restaurant. The upper right is a photo of Tanegashima Island. It's a really beautiful island. In the middle is a cultural exchange that we did where we got to do different things like learn calligraphy, and 2 of us got dressed up in Japanese outfits. It took like 3 or 4 women to get me dressed up there. On the bottom, I did have the opportunity to hike up Mount Fuji twice. The first time I got hypothermia and the second time I got altitude sickness. So that's when I learned that mountain climbing was not for me. Good thing I'm in engineering. And this last video will show you what GPM, what the launch looked like and what GPM looks like on orbit. So this is an animation, the rocket taking off. Boosters ejected. There it is on the final stage. Those are the boosters going down. Deployment of the observatory. Again, this is all in animation, showing the deployment of the solar arrays, beauty pass of those radars from underneath. High gain antenna. That's the GPM microwave imager starting to take data there. GPM's orbit, as George mentioned, those are the feed horns of the radar. 65 degrees inclination, it's about 407 kilometers. So one orbit is about 93 minutes, and there's 16 orbits per day. As George mentioned, it takes about 83 days for it to get over every single point on the Earth, but it does see most of the Earth about 16 times a day. And then my final photo is of the GPM team. This is taken at Goddard, and so this is a large number of the people who worked on the observatory. And actually, I think I see Dorian in the left in the back, and I'm pretty near the front in this.
Boy, doesn't that seem like yesterday, and also like a million years ago, Candace?
So that's it for my presentation.
That was an absolutely phenomenal presentation. I loved the fact that you were able to weave the personal stories and some of the ways in which you get to network with the people from other teams and from other countries. So thank you for sharing those. Those are always so interesting, and just imagining what it takes to pull off such a stunning feat of technology, to to pull all this together with so many people, and we're seeing the picture there of many of us who happen to be at Goddard. Of course, there are people from from so many other places, and in the that I shared with you, you will be able to see some videos about some of the various people who helped out with all kinds of different aspects of pulling the GPM mission together before it even launched. I know as I was sitting at Goddard Space Flight Center, I wasn't fortunate enough to go to Japan, but I was running a big event at the Goddard Space Flight Center Visitor Center. And I had my father, who isn't with us anymore, but he was there on one side and my brother on the other side. And we're watching the television, as Candace was talking about, and we're just watching. And I remember I'm holding both of their hands. And then I realized I was squeezing their hands really tightly. And once we saw that and heard that insertion was went well and it made it up, I just remember sitting there and just sobbing. And I know I wasn't the only one. So gosh, I know for the folks who are working with the PACE mission that successfully launched earlier this morning, very, very early this morning. It is such a scary time, and just also a time of absolute magnificence, particularly when all goes well. So thank you again, Candace. And now it is my great pleasure to have us finish off with Dr. Scott Brown, who was with us before GPM launched. And he's going to tell us about the precursor to GPM. He's going to tell us about the tropical rainfall measurement mission. And then he's going to fast forward to the future and tell us what's next. So take it away, Scott. You're looking good.
All right, thanks. Well, I guess I'll follow up with George and Candace. I'll give you a little bit of background. So I got a bachelor's degree in meteorology at a small program at San Francisco State University. Followed that up with a PhD at the University of Washington, 2 years as a postdoc at the National Center for Atmospheric Research. And then I've been at Goddard ever since 1997. I've had the privilege to be project scientist for the precursor mission, TRIM, from 2008 to 2015. I was actually project scientist for GPM from 2018 until about midway through 2022. And at that time was also working on what has become the Atmosphere Observing System, or AOS, which is a new mission in development that would launch toward the end of this decade, and then a second component in the early 2030s. So I'll cover that toward the end. So let's start off with TRIM. This was the precursor mission to GPM. Similar to GPM, it was a joint mission with JAXA in Japan. It launched in November of 1997, and it had a pretty comprehensive payload. It had the TRIM microwave imager, very similar to GPM's imager, that gives you the horizontal distribution of precipitation essentially in 2D, much like an X-ray. It had the first precipitation radar in space that gave a three-dimensional view of precipitation. It had a lighting imaging sensor so that we could, when we're looking at precipitations globally, we can see which storms were very electrically active. It had a visible and infrared scanner that gave us more information on the cloud properties. And it had a clouds and earth radiant energy system instrument that was basically trying to measure the way that clouds and precipitation interact with solar and terrestrial radiation. So TRIM's initial goal was to produce rainfall estimates on 5 by 5 degree grids on about a monthly time frame. But the long duration of the mission enabled us to go to much finer scales. And in fact, very similar to the Immerse product that George showed, TRIM was able to get down to rainfall estimates at a quarter degree at 3 hourly timescales. And so it was an amazing amount of progress going from the initial goals to what we have finally accomplished. So TRIM created a benchmark 17-year climatology for rainfall. That allowed us to get not only an accurate estimate of the annual global rainfall, but also to look at it by month over 17 seasons. And in this animation, hopefully it's not too jumpy, you should be able to see the northward and southward progression of the tropical rainfall bands as we progress through the year. The 17-year record also allowed for looking at variations of precipitation from year to year. For example, the impacts of El Nino and La Nina. And rainfall is associated with heating of the atmosphere when you get condensation and evaporation and other processes. And that the intensity of that heating is tied to the amount of rainfall. And that heating is really critical because it's a key driver of atmospheric circulation. And so TRIM provided some of the first estimates of those global heating rates. Now, TRIM flew in a 35-degree inclination compared to GPM 65. That meant that we cycled through all the times of the day in about 45 days, so a much faster time frame. And with 17 years of data, we could define the diurnal cycle of convection quite easily. And this animation shows the diurnal cycle as represented as if it was the same time of day everywhere. So times were shifted in order to have each frame represent a fixed time. And what you're seeing is then how the precipitation is varying over the day. So if you look at over the Rocky Mountains, you'll see the precipitation starting there, and then it moves eastward, typically as frontal systems or squall lines that eventually often reach the East Coast. If you look in the southeastern United States, you see that a lot of the precipitation actually starts offshore and then later on moves onshore, most likely associated with the land sea breeze type of circulation. And then if you look down at the mountains of Mexico, you can see that the precipitation really initiates when those mountains get heated up. And then as that heating goes down, the precipitation moves westward out over the ocean. And so we were able to describe this diurnal variation, not only over the US, but globally, and look at how it varies from place to place. And probably one of the biggest achievements of TRIM relates to tropical cyclone science. By having that 35-degree inclination, we were getting very frequent revisits of tropical systems compared to, say, a polar observatory that would only get 2 looks a day. We would often get 3, 4 looks a day. And the National Hurricane Centers and other operational centers would use the TRIM data to identify the location of the center. So, we would generate about 500 to 600 center fixes each year. TRIM provided some of the first global looks at tropical rainfall in tropical cyclones. Prior to that, most of our measurements were from aircraft measurements, mainly over the Atlantic, where we had regular reconnaissance. So TRIM started to reveal the vertical structure of precipitation within these tropical cyclones. In that animation, which will go again here in a moment, you can see these red towers. Those represent the deeper, more intense thunderstorms within tropical cyclones. And when they occur close to the eye wall of a tropical cyclone, they can actually lead to a rapid spin up of the circulation, whereas those towers that are further out tend to have less impact on intensity, but certainly do impact the rainfall that occurs with these storms. By compositing data over a large number of storms, we could determine what the profile of precipitation was as you go from the center of the storm out to larger radius, and see how that varies as a function of storm intensity, typically getting more intense with more intense storms. We could also look at how the environment, particularly through the change of winds with height, or what we call vertical wind shear, and how storm motion affects the distribution of precipitation around the storm center. Typically in strongly sheared environments, the precipitation becomes what we call very asymmetric, where most of the precipitation is on one side of the center and you'll have a lot less on the other. We also learned a lot about the eye wall and rain band vertical structure and how that related to electrification within these storms. And one of the unique things about the radiometer is that it had a very low frequency channel that allowed us to estimate sea surface temperature. And so for the first time, we were able to track the sea surface temperatures underneath the clouds, which normally would prevent you from seeing the ocean temperatures. And we could see these cold wakes that form behind the tropical cyclone as the strong winds of the storm basically mix up the upper ocean and bring colder, deeper waters up to the surface. Now, since tropical cyclones depend on warm sea surface temperatures, that had the effect of weakening those storms. And if it lasted long enough, it could potentially weaken storms that followed. So now I'll move to the Atmosphere Observing System, or AOS. It's a new mission that came out of the 2017 NASA Earth Science Decadal Survey, which basically tries to determine the Earth observing priorities for the next decade. And in this decadal survey, they identified aerosols and clouds, convection, and precipitation as some of the key processes that we needed to get measurements of. And so AOS is trying to get space-based measurements, that's the dominant part of it, but also some airborne and ground-based observations that are fundamental to understanding how aerosols, cloud, and precipitation processes are coupled and how that impacts weather, climate, and air quality. So why do we need AOS? Well, there's 3 themes I want to really hit here. One is climate sensitivity and feedback. So this is how aerosols, it's basically how climate impacts aerosols and clouds, and then how changes in those parameters feed back to the climate. We're also interested in convective processes and dynamics. So what are the vertical air motions that drive precipitation formation and convective storms? And then also aerosol processes and distributions. Now, aerosols and their interactions with clouds are key drivers of climate sensitivity. The plot on the lower left kind of gives you a sense of the observed trends in the gray and black for global temperature. And there's a fairly narrow uncertainty around that. And then the orange area is meant to show the projected trends and uncertainty based on a large number of runs of global climate models. And you can see that the planet is expected to continue to warm over time under our current release of CO2. But that with time, that orange envelope gets wider and wider because things get more and more uncertain. And a key driver of that growing uncertainty And the dominant source of uncertainty is aerosols and their interactions with clouds. So that's a key reason why we want to look at it. Aerosols on their own are important because they impact air quality and human health. A good example is the Canadian wildfires that occurred last summer that led to broad areas of dense smoke in the eastern US. And this type of thing occurs globally, and that has very harmful effects. Aerosols also have a big impact on aviation, particularly volcanic ash, that can damage aircraft engines. And so a lot of the times, if they can't accurately identify where the aerosols are, they'll either cancel flights or they'll divert the planes around the area where they suspect the aerosol is. And this can be quite costly. And then lastly, referring to convection here, there's been a nearly 7-fold increase in billion-dollar disasters in the US over the last 40 years. This is predominantly coming from convective storms and tropical cyclones. It's not all just because of the storms. A lot of this is growing infrastructure that's there to get damaged, but certainly increasing numbers of storms and increasing intensity of storm can be contributing to that trend as well. So next, I want to move on to aerosol distribution and processes here, because this is pretty fundamental, not only from the air quality standpoint, but because it also feeds back to how aerosols connect to weather systems. So this animation shows dust in the brown colors, sea salt in the blue to white, and smoke in the black to white colors. And you can see the evolution of these different aerosol plumes from these different source regions. So for dust, you see a lot of it comes from the desert regions, particularly the Sahara, and then moves westward over the Atlantic and gradually diminishes as it gets over the Atlantic. Sometimes these dust outbreaks are so bad that it actually significantly impacts the air quality in the Caribbean and in the southern US and even Mexico. The sea salt is the white, and actually at this point now, you can see these peaks in sea salt associated with a couple of storms. And that's because the sea salt gets emitted from the ocean surface by strong winds evaporating water from the surface, and that water releases sea salt into the air. And so we often see high concentrations of sea salt into these storms, and then as the storms diminish, those sea salt particles gradually decline. You can see it for these tropical storms as well as for extratropical storms. And then in the white, like over the US, it's kind of calmed down now, but at times you'll see these forest fires that are generating smoke, primarily in the western US. That smoke can affect the local area quite substantially, but you can also see that these areas of smoke can be transported very long distances. Now, those aerosols don't operate or don't exist in isolation. In this animation, the blues represent smoke here, in particular for South America and Central Africa, and then the white is clouds. And you can also see some of the brown associated with the Saharan dust. So these aerosols and clouds are occurring together. A lot of times, some of these cloud systems are forming right in the aerosol layer. Sometimes they're more on the edge of the aerosol layer, but the aerosol properties and the number concentration of these particles has a strong impact on clouds. So for a given amount of water that's going to get squeezed out in a cloud, if you have more aerosols, you tend to get a larger number of smaller drops that are less efficient at forming precipitation. And so you can get a longer lifetime of the clouds. When you have fewer aerosols, you tend to get smaller numbers of larger raindrops, or cloud particles, I should say, and that tends to more efficiently generate precipitation, removing water from the clouds and shortening their life cycles. And then all those microphysical effects within the clouds can strongly interact with solar and terrestrial radiation, and that's how it strongly feeds back to climate. And so AOS is trying to look at these coupled processes of how aerosols affect clouds, how the clouds develop precipitation, and then how that precipitation ultimately removes a lot of these aerosols from the atmosphere. And we're taking a multi-sensor approach here where each sensor sees a different part of the problem. They all have their shortcomings and their strengths. And so you have to take a multi-sensor approach. And these observations need to be obtained simultaneously, because when you look at this animation, you can see there's a range of scales, including very fine scales. And this is 1 minute imagery, and you can see how quickly these clouds are changing. So we need to be able to measure scales down on the order of about 1 kilometer or a few kilometers, and temporal scales on the order of minutes. The AOS mission is a very complex mission. It's 4 satellites, 11 instruments, and 3 international partners, Japan, France, and Canada. We have 2 orbits. There's a polar observing system called AOS Sky that is getting globally distributed observations that are particularly relevant to the polar regions that are most impacted by climate change. And then AOS Storm is 2 satellites in the inclined orbit that give us this diurnal variability of convection that we're really after to help us better understand convective storms. And with that, I think I'll stop there. Here's just a quick summary that kind of highlights some of the differences between the missions, but I'll stop there and let Dorian take over again. Sorry, I went a little bit long.
George, I'm sorry, Scott, you were just fine. This was perfect. I think this could be a really superb example, or this is a superb example of looking at something that when I was a classroom teacher, we talked a lot about, and that was, there was this big focus on STEM. You know, we've all heard of STEM, the science, technology, engineering, and mathematics. And what has been presented tonight just shows so beautifully the interconnectedness of all of these. You know, we had the TRIM mission, and that was so successful, and people were able to envision. Scientists had more questions. Those questions they knew could be answered if they had the technology. So then we had the engineers work with the technology, and it's just amazing. And now we see with AOS, okay, we've taken what, you know, the lessons learned from previous missions, and now what can we do with technology and engineering to bring that even further? And that's really how the process of science works. We don't ever just stop in one place. We keep on going, and each mission and each science question we answer should really then open up many more. So thank you so much, and thank you, Candace, and thank you, George, for just absolutely brilliant presentations. And what I'm going to do now is I'm just going to show you, let me come over here and share my screen. I'm going to show you what I have pulled together for everyone to go away with. This is your door prize. My job is basically to work as the connective tissue, to work with scientists and engineers, and to work with the various media professionals that we have, and then curate and collate things related to a certain theme. So what you have here, all under one URL, is a lot more information on the topics that we learned about. I started off here with a little more information about our 10-year anniversary, and I do hope that you will take a look at some of the upcoming webinars that we have. You just click on that button there. Each of those opens up a new website. And that you'll continue to join us and tell other folks about us as well. Here is some more information about the GPM mission. And this is the GPM website, and I explained how you go to that GPM website and scroll down, and that's where you can see the last 7 days of the precipitation data. These are a couple of really good videos that tell that the nuts and bolts, the hows and whys of the GPM mission. And then some educational materials as well, and some information on not only education, but even the publications, the peer-reviewed publications that have been and are continuing to be written using GPM data. Then I did a bit of a deep dive into some of the science, pulled resources together that talk about some of the science that we have learned from the Global Precipitation Measurement Mission. So you can scroll here, you can go to research topics and learn more. And since this is using websites, as there is more information that is added to these websites, this will always be kept current. This is our, I'd love it if you get a chance to do a deeper dive into the who's using GPM data. Those are a lot of different folks who are using our data, and we did a deep dive to find out what are they using the data for and how are they using it. And the results were really surprising. And we also did a lot of focusing on how did they get into their positions? What interested them? What education did they need? So then I pivot from that to going then next to the engineering side. So I have a lot of videos, and this is that GPM in a minute that Candace shared with us, and a lot of videos and some information on if you would like to pull together and make your own paper GPM model. I have the directions for doing that. If you want to make a Lego model, directions for doing that, and even some 3D printed models. So this again is just kind of like your one-stop shopping here to come and dive in and learn more, and also gets even some hands-on activities. For the TRIM mission, some basic information about the TRIM mission and a few videos and leading you to that website. And then you can also navigate using these navigation bars up here. I collected some information on the AOS mission that Scott was telling us about. And then I finished up by pulling together a lot of resources that give you some more insight into and some more access to resources that are related to NASA's Earth science missions. So I hope that you will, and I'll show you how to do that. Feel free to share right here. You can see how you can copy the link and share it in different platforms, and return to it early and often, and hopefully it will be helpful to you as you go forth, want to learn more, and want to share this with other people. So with that, I'm going to stop sharing. And just, I love the fact that people are continuing to be able to ask some questions in the chat, and that our scientists and engineers are responding to those. So I'll put the link to that resource packet I just shared. We will stay on a little longer for anyone who has questions, but we will officially end our inaugural webinar. And thank you again so much for joining us tonight.